Let me ask you one question. What is the most important technology in human history? My 6-year-old son says electricity. May agree or maybe thinking about things. How about computer? Artificial intelligence that drives for you or writing email for you? But human history tells something different. Stone created tools. Iron built empires. Silicon enabled the digital world. Every major leaps in human civilization started with new material. And what kind of new material do we need for now for the next human civilization? I want to introduce super material that we have been developed for years. Our company, AtoMe, is taking a new approach to the structural matter. Currently, energy industry is facing a critical need for high performance and better material that can withstand extreme temperature and tolerance, as well as more aggressive environment. However, existing material cannot keep the pace. A good news is that AtoMe has a super material that developed at MIT, combining metal with nanoceramic for better mechanical and thermal durability than ever before. This will provide essential solution in ongoing critical issue in climate change. And I want to share a story about new paradigm for metal design, future manufacturing at atomic scale. Let's talk about a little bit about climate change issue. It's not politics, just science. We may experience suspiciously hot summer all the time, or witness the strong storm. This extreme weather throughout all the globe. The question now is that how we get more energy, more work from every unit of energy. Because if we use the energy more efficiently, then we can reduce the carbon dioxide emission. However, the critical issue is the material. Material limit the performance of the machine. If we raise the limit, then we can use material smarter, not just more. What if we have a stronger, lighter material capable of tolerating high temperature? We can raise the ceiling of the performance. It's not just simply building strong in the lab, it's more real-world existential problem. That's where our super material came in and saved the day. So here, a material that can simultaneously withstand extreme mechanical load, high thermal load, or raging from storm, while staying lightweight. It can tolerate everything, maybe except a toddler with a crayon. So let me explain how we use this material. Power plant, if we run hotter temperature, then we can extract more power from same amount of the fuel. Geothermal, if we drill deeper and harder with material don't fail. And vehicle, if we have a light vehicle, we can travel farther with same amount of the energy. Durability, the component that lasts longer eventually save the energy and then waste. Amazingly enough, this super material can accelerate the fusion energy revolution. Its nuclear fusion promise clean, limitless power, but material is the limitation. It brings super hot sun on Earth, but the material today cannot host such a harshly conditioned object. Our company AtoMe is ready. Once we burn its fusion reaction sustainably, then we can, this age of carbon world will quietly fade into the history. So how did we do this? Let me briefly explain about science behind the background. We are here to learn each other together. And most of all, this is not described in any textbook. So let's dive deep in science. So what you are seeing is more like an atomic world. These circles are all the atom, and they are aligned. And what you see, there's mismatch of the atom is this location. And for centuries, this location activity has been orthodox theory governing how you understand math. This location is simple atomic rearrangement. They carry the strain and make a further material deformation. In traditional material science, if we resist the deformation, we call it strong. The idea of resisting deformation shaped everything we built. Iron for car, titanium for aerospace, aircraft. But the view of this idea has reached plateau. Most of matter has shaped with this same lens, what created limitation. Think of a group of soldiers in perfect rigid formation on flat prairie ground. As long as the ground is flat and smooth, the formation perfectly works well. But what happens if this formation has to go through mountains, valleys, or a dense forest? The rigidity also made it strong become a weakness. The formation brittle and unable to adapt. In reality, matter is now really flat flat parade ground. Inside the matter it has a full of irregularities such as dislocation, line tangle, or vacancy intersection microstrain, and so on. It's more like a wild landscape than smooth field. When we use our material in extreme conditions, the forces they experience are chaotic and multidirectional. In this scenario, adaptation is more important than rigidity. Instead of being locked into, behave like a rigid army, they don't need to move like a guerrilla force. Then able to adapt, move, flow in response to the stress without failure. And working with a colleague at MIT, we developed new model for the free volume. And in simple terms, it allowed the atom move with more flexible freedom than traditional atom. Instead of locked into the rigid structure, atom move more flexibly. Thinking about like a gorilla force moving through rough terrain. We shift, pivot, and accommodate stress response from different direction. In this scenario, the local force is not accumulated one spot and create a catastrophic failure. This sudden snap is exactly what happened in the traditional metal. This new type of atomic rearrangement that we study is something for the rheological deformation. It sounds a little bit complicated, but idea is simple. So think about slime that children sometimes play with. You can stretch, deform, and change their shape without breaking. Imagine metal that behave like this. You can stretch. The fluidity inside and then outside is strong. If metal has this kind of a nature, then it does not break. It kind of tolerate the higher fracture strength. We can validate this phenomenon through experimental test. Little bit of the background. In experimental, someone who may know from the engineering background, they hear about this tensile test. And the tensile test, there's the famous stress ductility trade-off. If we increase stress, then ductility goes lower. If we increase ductility, strength was lower. So engineer always need to choose between these two. But our data shows a little bit different. This data is the tensile, the stress strain curve. And what I want to point it out first, these two spots. One is the maximum tensile strength, y-axis is stress and x-axis is strain. And then this last spot is the fracture strength, is how much material tolerate before the break. Typically, in this material science community, they haven't been tried a lot to increase the strength without sacrificing ductility. But somehow, we break this traditional rule that we increased the strength and also we can increase the fracture strain. So now rules change. The material with the textbook need to rewritten again. Not only for that, if we use our theory into the aluminum has been popular in many different fields, but there's always drawback. Aluminum has a weak mechanical property than any other metal, like iron or titanium. But now using our theory, aluminum strength can reach to the mild steel, carbon steel, even full steel. So we couldn't observe this kind of phenomena before. So I would say, at least from now, from any physics breaking, really groundbreaking news. Yes. So this means engineer, they can build any component that is lighter, safer, and capable of tolerating at the high temperature. This kind of super material make the technology like a nuclear fusion practical. In other words, the material like this can turn the dreams of a star on Earth into industrial reality. And the impact goes far beyond the nuclear fusion. If material can survive such a harshly conditioned nuclear fusion reactor, they can survive almost everything. That put us in another frontier. On the ground. So we have been working with the oil and gas industry, partnering. And the point is that as we drill deeper in Earth's crust, the temperature and pressure ramping up so quickly. And traditional drill bit and well housing easily soften, deform, and get failed. But with our super material, the drilling system could operate harder, deeper, and longer. And previously, geothermal energy was not accessible, but with our material, we can tap into the Earth's natural heat as a clean and consistent energy resources. And also, extreme condition is not only found in nuclear fusion or deep earth ground. You can sometimes see we can found it in our own community. One day, I had a lunch with the criminology professor at Boston University, and I learned shocking statistics. Leading cause of the death of the children in United States is gun violence. It's not cancer or car accident. This is the very tragic reality. And I was wondering what we can do. And I realized soon that if super material can protect against damage from nuclear radiation, it can protect anyone from ballistic attack. We started to implement the nuclear material into protective armor. We use the same atomic principle to build the protective armor to create the system to protect the children. The idea is simple. The protection should not be burden to wear. The protection, this material need to absorb and redistribute the energy using our rheological deformation, the mechanism that we have designed for the extreme material. This is the simulation that demonstrate how the prevention of the bullet penetration in our thin plate, and this is the implementation, the concept implementation of our super material in the police patrol walk. And whether we contain the plasma at the million Celsius degree in fusion reactor or protect first responder from the dangerous situation, the underlying physics is same. We learn to control and dissipate energy to protect both nature and human life. That versatility lead AtoMe move so quickly from academic institute to the company that can create impact multiple industries. We are in a pivotal moment in our company history. We just monetized his finding, but the momentum is undeniable. We have a unique core team, all of them from nuclear department at MIT, and same academic family tree. Our CEO, Alex O'Brien, who used to be a student at the lab at MIT, and I'm CTO. And Kim Chan is Chief Commercial Officer, and Professor Julie, Chief Scientific Officer. Both Kim and Ju share the same advisor, and Ju was my supervisor when I was at MIT. We just, it's kind of family group. We share the same mission and move together. In 1945, the atomic technology contributed to the nuclear fission. Atomic bomb left tragic history behind. And now, in 2026, we learn to use this atomic technology to power the nuclear fusion. Atomic metallurgy, which is AtoMe, is leading that effort. We use its atomic world to build the foundation of next generation of human civilization. Not of age of resisting nature, but age of working with it. World needs smarter and stronger material to power for the future. That is exactly what AtoMe is doing now. Thank you.